Hi everyone, welcome back. In this video, we're going to break down resolution of forces in the simplest way possible, or my simple way. We'll look at how forces balance and how support carries load on a beam, and how to find the single force that replaces two forces. So let's jump right in. Let's start with this idea. If two forces act on a point that I'm going to be calling point P, all right, and the object is in balance, then we say that those forces must be one, equal, what equal in size. All right, so we're giving them a value, as well as they have to be opposite in direction. All right, now what does this look like? So we have our point P here, right? And we have a force that I'm going to be representing using an arrow. All right, and I'm going to be giving this a value, all right, which is basically giving it a size. So this would be, say, 5. All right, then I'm also going to be having another force acting down on that point here. All right, and this I'm going to also call it 5. In this case, we say that the object is in equilibrium. So this is in, so let me write this. This is in equilibrium. So what this is basically saying, it is saying that this here is what? Balance. So this is balance. All right. So this is the first resultant or resolution force that we're going to be speaking of in terms of a scenario. All right. So whenever we have a force acting down on a point or acting on a point, and we have another one acting on that same point, both values are the same and they're opposite to each other, then we say that they are in equilibrium or they are balanced. Basically, what is happening is that they basically cancel each other out. Now, here is something very interesting. If two forces are equal in size but not pointing exactly opposite to each other, all right, so let me see if I can show you what this is. All right, so if we have, say, a line here, all right, and we have a force acting down at this location here, so even though they're the same thing, let's say this is 5 as well, and then we also have another force acting somewhere here, and this is 5, so both of them are the same. All right, then the object won't be stable, because what is happening here, all right, because they're not acting on the same point. What is happening is that this 5 value here, and I'm going to say 5 as the size, is trying to push this side here down like a seesaw. All right, likewise, we have this force here is trying to push, all right, this side up like a seesaw as well. All right, now when this happens, the object won't stay still. All right, what is happening? Instead, it is being rotated, as you can see here. We call this scenario an unstable, all right, couple being this being 1, this being 2. So this here is said to be unstable. So this is an unstable couple, all right, opposed to the other one that was stable. All right, So this is an unstable force, if you want to think about it like that. No. Sometimes two forces act in the same direction and are parallel to each other. Now, what are we talking about here? Let me give you an example. So I'm going to still have my little seesaw line here, right? And I'm going to have a force acting down at this point and one acting down at this point as well. Let's give it a value or a size. Let's work with 5. All right. Then we're also going to have a force acting somewhere here in the middle. All right. And let's give this a size of 10. All right. I'm also going to have another example to my right here. So I have force acting down. Force acting down. Again, 5, 5. 1 here. 1 here. So both of these are also 5. Now, these are two different scenarios, but they'll give you the same result. All right. Now, what do I mean by this? These can be displayed by one single force, as you can see, that is equal in size and also parallel. This makes analyzing these two systems much easier. Now, if these forces are equal but opposite, all right, the objects stay in equilibrium. All right. Now, recall in the previous scenario that I gave, all right, where we said that it was unstable. The first one that I gave was stable. As you can see, this one that is here is more reminiscent of the first scenario that was given, which both are acting on the same point and the forces are the same sizes, so they basically cancel out each other. So these are stable. All right. This one over here now is somewhat similar to the second one. However, there's a twist to this one here, because on the previous one we did not have this side on it. So if we did not have this side, what will happen is that this will want to push down, this will want to what? Push up. All right. Now, that's not the case in this scenario. All right. Why this is so? This is because this is like we have a seesaw and we have the center portion of the seesaw and we have a guy over here and another guy over here. Both of them weigh the same thing. All right. So none of them is heavier than anyone. All right. So they won't be able to push down on one side and the other side won't be able to push down more than the other side. So they're both the same. So what is happening again is that both of these are basically acting in a similar fashion. So both of them are the same and they're equal distance apart in relation to the force that is acting up. Remember what I said about canceling each other out. So for example, this cancel this. This cancel this. That's very stable. All right. Now you'll realize that there's 10 here and there's 5 and 5. So this is what the canceling out is going to look like. So basically, this force will take out 5 out of this remaining 5. Then we have this other 5 here and then we cancel out. All right. So this is what makes it stable. So the upward force is the same as what is acting down as well. All right. So they're pretty much balanced. So that is how this force is explained. So this force is what? Stable. All right. So this is another scenario of a stable force. Now, let's talk about a common construction example. For example, a beam supported at both ends with a load right in the middle of it. Think about it like the walls in your rooms and your bed standing in the middle. All right, so this is a good example. Now let me draw something to kind of explain what I'm saying. All right, so I'm going to start off with my little, I'm going to say that this is the floor, giving it some thickness. All right, then I'm going to have a force on this side, aka my wall, and I'm going to call this RL, all right? Because this is the left hand side, that's why I have left there, RL, and this will be R, all right, for the right hand side. All right, in the middle I have my force, which is basically you are your bed. All right, and this here thing is basically, and I'm gonna sketch something here, are spaced out equal distance apart. Equal distance apart. All right, so these are the same. All right, and if we were to add values to this, so this is 5, giving that a value of 5. This also has a value of 5. This one has a value of 5 as well. All right, now what is happening here? All right, now because the load is at the center, the supports share the load equally. So let me just switch this one here. So this is going to be 10 instead. All right, so it is basically sharing this 10 load here between both left and right side. So this column here is carrying half of the amount. This column over here is carrying half of the amount as well. All right, so they're sharing the different loads. So this 10 here is pretty much cancelled out. So 5 cancel that out, leaves what? 5. Then we have that other 5 cancel that other 5 here. So it's basically in equilibrium. All right, if you want to think about it like that. All right, so in this case, this would also be what? A stable system. And I'm going to say system in this case. All right, stable system. All right, so this is another scenario that you will find. But no, what if the load is not in the middle of the floor or the slab or the beam? What do we do next? What am I talking about here? Let's examine this one here. Examine. So again, we're going to have a little thing that is going to represent our what? Our floor, beam, whatever it may be. Then we're going to have our wall, one wall on this side here, one wall on this side here. Let's give it a value. Let's say this is 9, and let's say this is 3. And again, this is R, L for left, and this is R for right. All right. Let's place our load. Let's say our load is somewhere along here, not in the center, because here is the center somewhere. All right, and we're going to give this a value of, let's make these both add up to that amount, say 12. All right, so that is 12 there, and it is acting down at that point. All right, so this is where it is at now. All right, so let's see where they're at. So that's where it is located. So it is a specific distance away from where RL and RR to the right and left. All right. Say this is, say, 2 feet from RL, and this over on this side is 6 feet from RR. All right. Now, in this scenario, we say that the supports that is closer to the load carries more of the weight. All right, I'm going to say that those 5, that 12 is the weight. All right, the further away, the less it's going to carry. All right, think about it as if you're carrying a long piece of wood, 2 of you. All right, and there's a bag tied on to a portion of it with some stones and a bunch of other stuff. The person that is far away will not feel the stones or the weight of the stone as much as the person that the stone is close to, if you want to think about it like that. So we have a guy here. All right, we have a guy over on this side here. All right, and they're carrying a 2x4, and they have something stacked on it like a bag or something. All right, now if the bag is closer to this guy over here, he is going to carry the majority of the weight. This person over here is carrying some amount as well, but not as much as this person. But if we move that bag to the center somewhere here, then they'll distribute it, so they'll be carrying the same amount of weight. All right, but if I move the bag closer to this guy over here, it means that he's going to be carrying the wood plus majority of the weight from this bag here. This person over here, not so much. If you have ever carried anything heavy upper stairs, you and somebody else, you'll realize that the person at the bottom of the stairs is going to be carrying the bulk of the load. All right, so that is what is happening on this side here with our little design here. All right, so let's see if we can continue. All right, so to find how much are the exact amount of load that RL on this side here will carry, and the exact amount that we have to carry over here, we'll have to calculate that amount. All right, we'll have to calculate it. Now, when we're calculating the values that we get, we call them reactions. All right, so you see these R that I have here, RL and RR, that is what this is here, the reactions. All right, so I wanted to take that into consideration. All right, now this is basically a ratio, if you want to think about it like that, depending on how far they are away. All right, so we can use these values to determine how much of the load RL is carrying and how much of the load RR is carrying. All right, so this is another scenario here. All right, next, let's look at how to combine two forces that act at a point. We'll call the combined force the resultant. All right, so remember that word all right, resultant. All right, remember that word. All right, we find it using either the triangle method, so two methods. All right, we have the triangle method or the parallelogram method. All right, now I'm going to be drawing two arrows with a shared starting point. So let's have this here. So this is my point, my starting point, and I'm going to call it P as well. All right, and then now I'm going to have some forces. So I'm going to have one forces acting this way, right? All right, and then I'm going to have the other force acting this way. All right, so both of them are literally pulling or tugging on point P right here. All right, now let's say that we're giving this some value. Say this has a value or a pulling force of 5. All right, and this has a pulling force of 6. All right, so we have force 1 here, and we have force 2 here. All right, so this is it. So this gives two forces that are acting at one point. So what do we have here? We have two forces. All right, two forces. So we have two forces acting at what? A point. All right, so we have two forces acting at a point. All right, now what do we do here? All right, to find out what is happening here, we'll first draw the first force to scale. All right, now whether you're using a software or using ruler, you have to decide on your scale. You could say for every one of this unit here, so for every one unit, so we can say for every 1 unit, that will be equal to, say, 2 centimeter on my paper that I'll be drawing. All right, or you could say for every 1 unit, which is these 5 and 6 there, we could say that it's equal to 1 centimeter as well. You decide on the scale that you want. It could be 1, 2, 3, 4, 5, 10, 1.5. You decide on the scale. All right. Oh, you're going to be doing it. All right. And in the future, when we're doing questions in relation to these, you'll see what I'm talking about even more. All right. So you'll draw the first force to scale. All right. So I'm going to say that this first force here, which is 5, all right, we'll say that this is, say, 5 centimeters. So from here to here is 5, because we're using a scale of 1 to 1. Scale 1 to 1, all right, to make things simple. So from there to there, because we're using a scale of 1 to 1, this is now 5 centimeter. All right. So we have our force there. All right. So this is F1. All right. Then now we will now connect the start point. So we're going to, so once we have the first point, we're going to draw the second point. Now the second point is going to be coming from the end of F1. All right. So we have, this is F1 right here, and this is F1 right here. Now for F2, F2 is going to be right here, starting at F1, going in the same direction as it is going on the drawing here. And again, we're using the same scale. So for example, this now will be 6 centimeter. All right, this would be 6 centimeter. All right, now we have the two forces in the order that they fall. All right, so we're basically doing a head and tail. All right, and in future videos you'll see these panning out. Now once you have done so, you're going to connect, all right, the start point to the end point. What is the start point? This here, point P, is your start point. Your end point is right at the end of what? Force 2. This is your end point. And what are we going to be doing? We're going to be connecting these 2 points. And you realize that it basically creates a little triangle. All right. Now that final line is the resultant. So this is the resultant of these 2 forces. So this is what? Your resultant. And I'm going to say resultant line right here. All right, just for clarity. But guess what? It is resultant. All right, so that's your resultant. Now this resultant shows both the size and the direction of the combined forces. So for example, we can now use this line to determine what the force is right here that will be canceling out everything. All right, because all we need to do is to measure the distance from here to here using our ruler or whatever device that we have. And this is why we do it to scale. So say for example we got say 10, right, or 11. All we'll do, we'll use our scale. So if it is 10, right, and if it is 10 in centimeter, and we're using a scale of every 10 centimeter is 1 unit, then it means that this line here has to be 10 of whatever it is, whether it's whatever force, Newton, kilonewton, and you will get to that in the future. All right. So if we had used a scale of 1 to 2, then it means that in this case it would have been 20. All right. This would have been 10. This would have been 12. All right. So this is how it basically works. Now let's finally talk about the equilibrant. So let me just write this here. It is called equilibrant. I'm trying to pronounce this one here. Equilibrant. All right, so equilibrant. All right, so we're talking about equilibrant now. Now what is this exactly? The equilibrant is a force, all right, that is equal in size to the resultant, but pointing in the exact opposite direction. All right, let me see if I can explain this to you. Say we have a force acting in this direction, right? Right, and we have another force acting in, say, this direction. All right, so that's another force, right? And we know we did the resultant, which will be basically connecting the start point to the end point. All right, now you'll realize that both of these forces are all acting in this direction. All right, all right, the equilibrant is what is going to cancel it out. All right, so it means that the canceling out has to be going in what, the opposite direction, all right, for it to be an equilibrant. All right, now how do we indicate this on our drawing or on our force diagram? We simply place an arrow to say where it is going or where the force is going. So for example, it is going back to where your start point. All right, so that is basically your EQ, which is your equilibrant. All right, so that is that there. So we have our forces here, F1, and we have F2, force 1 and force 2. We have our resultant, all right, and then we have our equilibrant, which is basically pointing in our directions. All right, so the equilibrant would basically bring the system back to being balanced, being stable. And remember, when you draw a vector, because this is technically a vector quantity, all right, when you draw a vector, the arrow should follow a head and tail fashion. So for example, head, and here we have the tail. All right, so it's always follow that fashion. So you literally be connecting them around. All right, so we always follow that head and tail fashion, and in other videos you'll see how those develop. Now this helps to show how the forces flow and combine with each other. All right, so that is it for these series of scenario based forces and how they will literally interact with each other. And that's it. You now understand the basics of resolving forces, beam reactions, resultants, and equilibrant. If you found this helpful, don't forget to like, subscribe, and share with your classmates. Alright, don't leave anybody behind. Alright, thanks for watching, and I'll see you in the next one.